here. It's actually just a really complex physics. Like just higher issue rather than paying I'm just never gonna do for that coding ever again.
Okay, so it's time to go ahead and get started. So today's lecture is probably going to run a little longer than the lecture last week. So when I hit the top of the hour, if I'm still lecturing, we can take a short little break if you want, or we can just plug along. But then after the lecture portion, I talked about this last week, the format of the class. Then there's an activity on what the lecture is going to be about. And then you'll have time at the end to work on Lab 0. Now, Lab 0, recall what we talked about last time, that's due tomorrow night at midnight. Now, if you weren't able to load Vivado onto your computer, again, we have computers in the back that you can use. If you're waiting for your board still, I counted 5 boards back there, and then I brought mine, so we got a total of 6. Also, when we get to the lab portion, you're not required to, stay here. If you want to go work somewhere else, and we want to go back to your dorm, like some people, they have Vivado on their PC at their dorm because they have like a Mac laptop, but they have a PC desktop. So, if you're in that situation, or if you just work better somewhere else on campus, that's fine. Okay, but remember, you do have to be here for the activity. To get credit for the activity, you do have to be physically present. Okay. All right. So we got quite a agenda. We're going to start talking about what the basic logic gates are, and then from there, we're going to look at various forms of how to express, a digital circuit. Now, on each table, there should be this handout. This handout has what are called truth tables and what the logic symbols are for our basic gates that we're going to be talking about. Also, there's a bunch of Boolean identities and axioms. Boolean is just a fancy word for base 2 algebra. And I'm not going to go over everything that's on this handout. I made this handout available more as a reference. Okay, but there are some things that we're going to discuss. Okay. I would recommend taking a picture of this because I only put one handout on each table. And then also on each table, and there should be enough for each student, is the activity. Okay, and also the activity answers are posted up there on the wall. Okay. All right, but let's talk about logic gates. And the first logic gate we're going to talk about is the NOT gate. Okay, the NOT gate has this symbol. It's an arrow with a little circle. This is the input side. And this is the output side. And in Boolean algebra, just like base 10 algebra, we use variables. So if I label this input A, okay, input A, well, in Boolean algebra, we would represent the output of this NOT gate as the same variable as the input, but with a bar over it. Okay. And in Boolean algebra, that bar means opposite. Okay. So the output of a NOT gate is just the opposite of whatever the input is. And logic gates have binary inputs. And a truth table is a table that shows you what the output equals for every possible input. So since this NOT gate just has a single input that's binary, okay, that's either a 0 or a 1, there's only 2 possibilities of inputs. It's either a 0 or a 1. And the output is opposite. So opposite of 0 is 1, opposite of 1 is 0. Okay? So that's our first logic gate. Now, before we go any further, I want to tie this into circuits. Okay. I think I mentioned to some people last time, I don't know if I told the whole class, but I used to work for the EE department. And when I worked for the EE department, I mainly taught circuit classes. I taught this course also, but I taught a lot of circuit classes. Now, since I switched over to CPE, I'm just teaching CPE courses. But if you ever have a circuits question, I can help you with that. Okay. And nothing circuits related is testable in this class, right? But sometimes I like to mention circuits and tie it into this class a little bit, just because I like circuits. And also, I think it's a good idea just to see or show you that, you know, other classes you're taking ties into this class. So these zeros and ones that we represent inputs and outputs in digital circuits, they're voltages. Okay. You know, you take a circuits class, first day of class, you usually talk about what voltage is, right? So you see, ideally, again, this isn't testable, but you may find it curious. Ideally, a zero is typically 0 volts. And ideally, typically, a 1 is 5 volts. Okay, now that can vary. I mean, when you take your junior level, like electronic classes, you're gonna learn that there's all different kinds of what we call family of gates. And depending on the particular family of gate, those voltage levels can differ, okay? But the key point is the 0 is gonna have some voltage and the 1 is gonna have some other voltage. And often the 0 is represented with 0 volts because when you design a circuit, it's easier to design a circuit where you just have to detect whether there's voltage or not, as opposed to 2 different voltage levels, okay? Now that's ideal. In actuality, how many people have taken a circuits lab? Some circuits. Oh, great, a lot of people in this class. Well, if you've ever taken a circuits lab and you go to measure voltage in a circuit with a voltmeter, you know, a multimeter that's the voltage. Typically, does that voltage stay nice and steady for any significant amount of time? No, what happens when you
It like fluctuates a little bit.
Yeah, it's gonna fluctuate a little bit, if for nothing else, due to thermal effects in your circuit, right? Because as current flows through a part, it heats up a little bit and it changes its parameters, like it can change its resistance a little bit, it changes the current going through it, which by one's law changes the voltage, right? So voltage typically will fluctuate some. So you see, in actuality, a 0 is a voltage that's beneath a certain amount that we call a threshold. So typically, you know, a 0 will be below, a voltage below a certain amount, and a common one is 1.4 volts. Okay, there's a family of gates called TTL, and for that family of gates, a 0 is red if a voltage is less than 1.4 volts, and it's a 1 if the voltage is above 1.4 volts. And if you're hovering at 1.4 volts, well then flip a coin to see whether it's a 0 or a 1. Okay?
Is there a reason that they selected those numbers? Or is it just arbitrary?
Well, this 1.4 volts comes from the electronic circuitry, and I'm going to show you an example of that coming up. But it comes from a particular electronic circuitry that's used for that family of gates. You know, 1.4 volts is for TTL, but there's another family of gate called CMOS, which it's a different voltage level. In fact, there you have some flexibility. So TTL is very rigid.
It's almost like a valve that has a spring, particular flow requirement.
Yeah. Although again, we're not talking current here. Yeah, we're talking voltage, which is more like a pressure. So like a pressure valve, if you will. Yeah. Okay. So anyway, like I said, I'm not going to test you on this, but just so you know, I think it gives some tangible meaning to these 0s and 1s. They're just a convenience to represent voltage. Okay. All right. So this is our NOT gate. Any questions on the NOT gate before we move on to the next gate? Okay, NOT gate is also called an inverter. Okay, just another word for the same thing. Okay. All right, so moving on. The next gate we're going to look at is the AND gates. Okay, and the AND gate has this symbol. And again, typically we identify the inputs and outputs with variables. I'm gonna label my inputs A and B, but you can use any variable. And I'm gonna label my output F. And in Boolean algebra, and is either written with like nothing in between the variables. See, this output here, this equation, this is read as output F equals A ANDed with B. Okay, also, you can see sometimes that they'll use a dot for an and. Okay, so both of these mean output F equals A ANDed with B. Now, what does and mean? Well, let's look at the truth table. Okay, like I said earlier, a truth table will show you what an output equals for all possible inputs. So if you only have one input, there's only two possibilities since each input can either be a 0 or 1. How about if I have two inputs? How many possibilities could I have? Like how many unique combinations of 0s and 1s can I have if there's two bits? 4. Right, 4. Because both bits could be 0, or you could have 0, 1, or you could have 1, 0, and both bits could be. Right. How about if I had 3 bits? How many possible combinations of 0s and 1s? 8. 8. Right, it'd be 8 because they could all be 0, or you could have this, 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 or you could have this. 0, 1, 2, 3, 4, 5, 6, 7. See, I'm just counting in binary. So 0 through 7, 8 possibilities. How about if I had 4? 16. What if I had 5? 32. What if I had 6? See the pattern? Right? Every time you add a bit, you double the number of possibilities, right? You double the number of possible combinations. This is probably one of the most important relationships in this class. The number of values that you can obtain from the number of bits is equal to 2 to the number of bits. Right, so if I have 1 bit, 2 values, 2 bits, 4 values, 3 bits, 8 values, 4 bits, 16 values, and so on. Right, every time you add a bit, you double the number of possibilities. Okay, this comes up again and again. Eventually this will be ingrained in your brains. Okay, so yeah, write that down. Come on. Okay, but now getting back to this. What do we mean when we and? Well, it means this. It means that in order to get a 1 out of an and, I need all inputs to be 1. If at least one input is a 0, an AND gate's going to output a 0. Now, this is a 2-input AND gate. But you can have 3 input AND gates, 4 input AND gates, 16 input AND gates. You can have as many inputs to an AND gate as you want. No matter how many inputs you have, it's always true that all the inputs have to be a 1 to get a 1 out of an AND gate. If only one input of, no matter how many inputs is a 0, you're going to get 0 out. Okay? So the truth table tells us what's meant by these logical operations. Okay? So any question on the AND gates? Everybody good? Okay, let's do an OR gate. Okay, here's the symbol for an OR gate. It's more streamlined, if you will, than the AND symbol is. Aerodynamic. Yeah, aerodynamic. Like a spoiler. Okay, so that's the OR symbol. Oh, question.
Sorry, I want to ask the not be.
Okay.
So when is it going to invert it like say a negative 5, or will it bring it down to 0 volts?
Well, if this are the possibilities where 0 is 0 volts, if you put a 1, which is 5 volts, you'd get 0 up. Now, there is a family of gates, or well, you could have what's called CMOS, where the possibilities are 5 plus 5 and minus 5. Like there is that type of circuitry. And if that was the case, you put 5 volts in, you get minus 5 volts out. But for what I'm using right here, you get a 0 out, 0 volts out if you put 5 volts in. So, yeah. Okay. All right, the OR gate, the Boolean algebra for an OR gate looks like this, that the output would equal A ORed with B. So notice in Boolean algebra, the plus sign doesn't mean add. Okay, this means OR. Okay, and what OR means, we can look at the truth table for an OR. Okay, with an OR gate, it only takes one input to be a 1, and you'll get a 1 out. The only time you get a 0 out of an OR gate is when all the inputs are 0. So you see the truth table for an OR gate would look like this. And this is true no matter how many inputs you have. You know, you could have 2, 3, 4, 16, no matter how many, as long as at least one of the inputs is a 1, I'm going to get a 1 out. I only get a 0 out of an OR gate when all the inputs are 0. Okay. So any questions on the OR gate? Now, these are the gates that are on that handout. Right? There's 3 gates with 3 truth tables, but there's 2 other gates I want to go over that's not on the handout. One of those other gates I want to go over is called a NAND. NAND is short for not and. And the reason why we say it's not and is because a NAND gate is equal to an AND gate with an inverter on the output. And the symbol for a NAND gate looks like this. So you see the symbol for an AND, it's just like the AND, but it's got this little bubble on the output. And I think the reason why they chose this symbol for the NAND gate is because since it's equal to an AND with an inverted output, it's almost like the inverter is kind of squished into the symbol, but we leave the little bubble showing. Just that little bubble tells us that the NAND is an AND with an inverter on the output, because that little bubble comes from the inverter. Okay? So the truth table for a NAND is going to have an inverted output from what the AND does. So here's our truth table for the AND, right? Remember, an AND only gives us a 1 out when all the inputs are 1. Well, because there's an inverter on the output of the AND that makes the NAND, a NAND will only give you a 0 out when all the inputs are 1. Otherwise, you'll get a 1. So you see, if you compare the truth table of the AND to the NAND, the only difference is that we have inverted output here, right? That makes sense? Now, the Boolean algebra for an AND is that since we're ANDing and then inverting, well, as we said earlier, the Boolean algebra for the AND is going to just be the AB with a space, or you can put a dot there. Well, then the AB ANDed all gets inverted. The whole thing gets inverted. You see, that's the Boolean algebra for an AND. Does that make sense? Okay. Any question about the NAND? What do you think's next? OR. Right, because if you can invert the output of an AND, you can input the output of an OR, right? And that gives you the NOR. Okay, which is not OR. So that's the same as an OR. The output inverted. And the symbol for the NOR it looks like that. And then the truth table, well, it's just what we had for the OR, but with the output inverted. right? So here's our or, where remember with an or, you get a 1 out as long as at least one input is a 1. Well, with the nor, you get a 0 out if as long as one input is a 1. So you see these are all going to be 0. And you only get a 1 out of a nor when both or all inputs are 0. And then the Boolean algebra, well, you're ORing and then you're inverting. So the output of a NOR would look like that. The Boolean algebra would look like that. Okay. Now, before we go any further, again, just some circuits, which again, you're not going to be tested on. But let me see that handout there, please. So this same handout that has the, these basic gates with their truth tables and some axioms and theorems. If you flip it around, there's an example of electronic circuit for a NAND. So you see this symbol, this NAND gate symbol represents electronic circuit like this. And you can see there's, well, for those of you that have had maybe a little bit of an advanced circuits where you know what a transistor is, that's what that symbol is, a transistor, and you got a couple of diodes and a few resistors. And again, the only reason I show you this is just so you know that these symbols represent actual tangible circuits. Because you're going to see that as we go along in this course, we're drawing all kinds of gates and stuff, and it can seem like really abstract. Like, oh, what are these pictures doing? But these pictures, these diagrams represent actual circuitry that you can build. Okay, so this was logic gates, and electronic circuit was just that example I just showed you. The next thing to talk about is one of the theorems that is on that handout that you have, that reference handout I have called DeMorgans. Okay, but before I move to DeMorgans, do you have any questions up to this point? All good? Okay, so let's talk about DeMorgans. So if you look at the handout that you have, that your table has, DeMorgans is the one right at the very bottom. Okay, and there's two parts to DeMorgans. One part is 15A, the other part is 15B. Looking at 15A, what is that telling us? It's telling us that we have an equality. But what is it telling us that's equal? Because what do you see on the left side for 15A? What is that on the left side? That's the Boolean equation for what? A what? NAND, right? See how X and Y are being ANDed together, right? The little dot means AND, then the whole thing inverted, right? So that's what we have here, except we got AB instead of XY. So you see on the left side, that's a NAND gate, and it's telling us that it's equal to input X inverted ORed with input Y inverted. And then 15B, what is that telling us? NOR, a NOR, that's what's on the left side, is equal to inverted X ANDed with inverted Y. Okay, so you see DeMorgans tells us these two things. See, there's two parts to it. That's the Boolean algebra. In symbols, I could write it like this. That a NAND is equal to an OR with inverted inputs. And then the other part of DeMorgans tells us that a NOR is equal to an AND. Okay, so I just wrote in symbols what's on that reference in Boolean algebra. A NAND's equal to an OR with inverted inputs, and a NOR is equal to an AND with inverted inputs. And the way you could prove this, in fact, let's go ahead and prove one of them. Okay, we'll prove this one, that a NAND is the same as an OR with inverted inputs. Well, the way to prove it is, we already did a truth table for the NAND, right? Here's our truth table for the NAND. Well, if these are equivalent, this OR with inverted inputs will give us the same truth table. Right? So you see, if I do a truth table for this, so A, B are on this side of the inverter. That means we're going to have not A and not B on the other side of the inverter. In fact, let's put not A and not B in our truth table too. Yeah, I don't think I mentioned earlier that by convention in truth tables, we put the output or outputs, because you'll see later on in the course that, you can have, a truth table that has more than one output. Here we just got one output, but if you had multiple outputs, you would still put all the outputs on the right side of the truth table, and you always put inputs on the left side. Okay, so the reason I included the not A and not B is because we got these inverters, and A and B get inverted before they get OR. Okay, so we have the same values for A and B as we did, here for the NAND gate. They get inverted. Let's see, so 1 1 1 0 0 1 0 0. And then not A and not B get OR. And remember, for an OR gate, it only takes a single input being 1, as long as one input's a 1 to get a 1 out. So you see, these would all be 1, and we'd only get a 0 out when both inputs are 0. So you see, when we do the truth table for this OR with inverted inputs, it gives us the same truth table as the NAND does. And that's why we say they're equivalent, because they have the same truth table, right? If you're getting the same output for, all possible combinations of inputs from two different circuits, well, that means the two circuits are logically equivalent. Okay, and you could do the same thing. In fact, on your own at some point, you could do the same thing. Take this AND gate with the inverted inputs, do the truth table, and you should see that you get the same output as what we did for the NOR. Okay, but I'll leave that for you to do. Okay, it's not, I'm not going to collect it or anything, but I think it's a good exercise just to prove it to yourself at some point. Okay, so any questions on DeMorgans? Because now we're going to use DeMorgans. Okay, we're going to actually put it to use, but I just wanted to show you, why these are equivalent. Okay, but any questions up to this point? All right, so we're done with DeMorgans. All right, so now I'm going to go ahead and erase this. So What's that? Well, remember, this is, well, do you mean the proof? Well, I was gonna, well, I guess I got room over here. Yeah, I can leave it. I'll leave it. Let me move the camera. And I'll pick up over here. I'll leave it up there. We don't have to erase it. All right, so let's move this camera. Let's see. Right about here would probably do. No, actually, I can go further here. All right. We'll go right about there, I guess. So where's my field of view then? Here, so remember, just like I said on Thursday, if I ever get to this place and I don't move the camera, please yell out and move the camera. Sometimes I forget. All right, but the next thing we're going to do is we're going to look at a truth table, and then from that truth table, we're going to get different forms of Boolean equations. One's called SOP, called POS, and I'll explain what these acronyms mean in a little bit, okay? But first, the truth table we're going to use is this one here. I'll explain what these variables are. This is a C, variable C. This is G. This is S. And I'll explain what the variables mean in just a second, but since we have three inputs, again, that are digital, right, can either be 0 or 1, how many possible combinations? 8, right, 2 to the 3. Because I could have all zeros, right, which is the same as a binary 0. I could have 1, 2. See, I'm just counting in binary. See, also by convention, when you make a truth table, you put your inputs in binary order. You know, they might not represent binary numbers, but we still think of them as binary numbers when we read the truth table. I always double check because it's easy to miss one. So 2, 4, 6, 8, right? 0, 1, 2, 3, 4, 5, 6, 7. Okay. All right. In this example, C stands for chips, like tortilla chips. G stands for eggs. And S stands for salsa. And E stands for eat. And this truth table is based on my appetite. Chips, egg, salsa. So a 0 means we don't have it, and a 1 means we have it. A 0 out means I wouldn't eat it, and a 1 means I wouldn't eat it, right? So if there's no chips, no eggs, no salsa, there's nothing to eat, right? So I mean, that's obviously 0 output. My appetite, I don't like salsa by itself. I guess there's people out there that like salsa alone, but not. Eggs, just eggs. Yeah. I love eggs, all kinds of different ways, scrambled, fried, all kinds of eggs. Eggs and salsa is like one of my favorite things. I love eggs and salsa. How many people love eggs? Yeah. How many people think it sounds gross? Yeah, I did too at one time, but I had it and it's great. My brother, well, actually, I should probably tell you, I have 3 brothers and 2 sisters, and they're all like way older than me. I was definitely my parents' late in life mistake. Well, I mean, it's the truth. And my next oldest brother, he's like 7 years older than me. He used to put ketchup on his eggs, like it's scrambled eggs, ketchup. You know, as a little kid, I used to think that was so gross. I still think it's somewhat gross, but I mean, salsa's kind of, you know, it's got tomatoes and stuff, you know. Still haven't tried the ketchup because it just doesn't look good to me. Anyway, eggs and salsa, very good, love it. Tortilla chips just by themselves, yep. Chips and salsa, of course. Chips and eggs, nope, not a fan. And adding chips to eggs and salsa, not a fan. Okay, so this is a truth table showing what I would eat based on the combination of these ingredients. Okay, and from this truth table, we're going to get 2 forms of Boolean equations. We're going to get what's called an SOP form, and then we're also going to get a POS form. We're going to start with SOP. SOP for E. Okay. SOP, this is the SOP equation for what I would eat. You could also do an SOP for what you wouldn't eat. That would be SOP for not eat, right? Because the E means what I'm going to eat, that's where there's a 1. And not E then would represent what I wouldn't eat, which is a 0, okay? But this is SOP for E. And SOP stands for sum of product. And this is how we get an SOP equation directly from the truth table for E. We look at where the output is equal to 1, and then we write each combination as a term in that equation. So starting here, okay, I'll eat if they're just eggs. And when we write a variable, just the variable, that means the variable is a 1. When the variable is a 0, we put a bar over it, right? Because again, a bar in Boolean means opposite. So if I call just the variable 1, that means the bar over the variable means not that variable, which is a 0. So see, this row of the truth table would give us, as a term, it would give us not C, because C is a 0, G, because G is a 1, and then not S. Right, because this combination, I just have eggs. And if you have it, there's no bar. If you don't have it, there's a bar over it, because that means you not have it. Does that make sense? Okay, well, if that makes sense, we're just going to continue on here, because I'll eat this combination, or I'll eat this combination, or I'll eat this combination, or I'll eat this combination. Okay, so now before I write this next term, I put the or symbol. Right, and then I just do the same thing. I don't have chips. I have eggs. I have salsa. So you see, I'll eat if there's eggs. I'll eat if there's eggs and salsa. Okay, I'll eat if there's just chips. So that term would look like this. Right, because I have chips, I don't have eggs, and I don't have salsa. And I'll also eat if we have chips and salsa. So that would be. And you see, this would equal E, right? Because these are the combinations I would eat. Now, I could also write SOP for not eat, right? The combinations that I wouldn't eat. And the only difference would be I'd have E bar, right? And then I would just write the terms for when the output is 0. Okay, we're going to do that later on. Okay, but I thought I just mentioned it now. Okay, but did everybody see how I got this SOP for E, right? I'm just looking at where the output is a 1, and I'm just writing the combinations, putting the variable if it's a 1, putting the not variable if it's a 0. Now, the reason they call this sum of products is because if you were to look at this as a base 10 equation, that's what it would look like, right? Because these are being multiplied together, right? If it's a base 10, and then they're being added together. But that's not what's going on here, because this is base 2. You know, these terms are being ANDed together, and then the terms themselves are being ORed together. Okay, but we call it sum of products because if you took it as a base 10 equation, that's what it looks like. See, in fact, sometimes people will say that AND is the logical multiply and OR is the logical addition. Okay, and that's just because of how it looks if you were to consider it to be base 10, but it's not base 10, it's base 2. You know, OR doesn't mean add and doesn't mean multiply, right? It means these things in the tables that we talked about earlier. Okay?
Why is this useful for us? Like something all the place.
Well, you're going to see that to come up with like a tangible logic circuit. In fact, we're going to get the circuit diagram here. You often start with the truth table, and then from that truth table, you get the Boolean equation, and then from that equation, you can get the circuit. So it's part of a process. One of my digital professors way back, Professor Corey, I remember him saying that if you want to design any sort of digital circuit, draw a truth table first. If you can put something in a truth table, you can get a logic circuit. But yeah, it's part of a process. And SOP, that's one form of logic circuit. And I'm going to show you the diagram for an SOP in a little bit. But the next thing we're going to do, and I think this will take us to our break, is we're going to come up with a POS. Right, product of sums. Thanks. Yeah, product of sums. Okay, we're going to do a POS, and we're going to get POS for E. Because you can also get POS for not E. Just like you can get SOP for E or not E, you can also do POS for E or not. Okay, but we're specifically going to get POS for E. And this is really important, okay, because this is something students often forget or miss. And that's, if I want to get POS for E, you start with SOP for not. Okay, now just take my word for it, and then I'm going to show you a derivation here, and you'll see at the end why this is so. But in your notes, highlight, put a star, whatever you have to do, that if you want POS for E, you've got to start with SOP for not E. And the reverse is true too. If you wanted POS for not E, you would have to start with SOP for E. Okay? All right, but again, we're doing this example here, POS for E, so we're going to start with SOP for not E. So this is where I'm going to look at my truth table, and I'm going to look at where the zeros are. And I'm going to write my terms for where output E is 0. So output E is 0. Well, actually, let's write here. Looking at zeros. Looking at E equal to 0. Okay. So I'll have not C, not G, not S, right? Because I don't eat if I don't have any ingredients. I don't eat if there's just salsa. I don't eat if I have chips and eggs. Oops, we have it, so you bar. Chips and eggs. And I don't eat it if we have all three. Okay, so any questions on how I got this SOP for not E right? It's the same thought process as getting SOP for E, except I'm looking at where E is 0 instead of when E is 1. Okay, and again, this is what we have to do first if we want to get POS for E. Okay, the next thing we're going to do, and this is part of the derivation, is that we're going to go ahead and we're going to knot both sides of this equation. So let's see, I would do this in a different color. So I'm going to knot this side, and I'm going to knot the other side, the whole thing, right? Because if I knot both sides of the equation, I haven't changed anything. Okay. All right. So if you have a variable that's been knotted twice, right? That's like putting either a 1 or a 0 through 2 inverters in a row. It's going to come back to the same thing, right? If you double knot something, it just equals that variable. Doesn't that make sense? So you see, this is just going to be E. Okay, so now comes the part where we're going to use part of DeMorgans. Okay, remember, there's 2 parts of DeMorgans, right? One part tells us that a NOR gate is the same as an AND with inverted inputs. Well, can you see that if I take this combination as an input, and I take this combination as an input, and I take this combination as an input, and I take this combination of an input, look what we have. This combination is ORed with this combination, that's ORed with this combination, that's ORed with this combination, and the whole thing's inverted. So can you see that this is a NOR gate where the inputs are the combinations? Can you see that? You see this right here, the NOR. It's a NOR with this input, this input, this input, this input. And DeMorgans tells us that a NOR is equal to an AND with inverted inputs. So I take each one of these inputs, right, these combinations, invert it, and then AND them together. So you see DeMorgans, this part of DeMorgans, it would give us this. I take this input here. Invert the whole thing, right? Because I'm taking that input and inverting it. And I do the same thing for each of these, right? I take the combination, which is the input, invert the whole thing, and then I AND them. That should be, sorry. So let's see, we got the end. Let's see. ANDed with Oh. That's what are we here? Oh, lost track. CES. So let's see, did I make, keep an eye on me. If I make a mistake, let me know. So you see what I'm doing here? I'm taking each combination because each combination is an input and I'm inverting it. So I took this combination, inverted it, this combination, inverted it, this combination, inverted it, this combination, inverted it, and then we're ANDing them together. So you see, this is the NOR equaling the AND with inverted inputs. Okay, so there's another step coming up, but before I do that, does everybody see what I did there? Right, do you see I'm using this part of DeMorgans? Right, we had a NOR expression, and now I'm turning it into an AND with inverted inputs. Everybody okay? All right, now the next step is look at each one of these terms. Like, what is this here? If you consider C, G, and S being inputs, what's going on right here? A NAND, right?
So when you say this is equivalent to that, so you're saying, for instance, you'd say A, not A plus B is equal to not A dot not B.
Well, I mean, you're talking about this specifically here?
Yeah.
You're talking about the step before? What I'm saying is, first of all, well, let me ask you. First of all, can you see, just looking at this right here, can you see that this is a NOR gate where these combinations are the inputs? Does that make sense to you, just looking at this? To see how it's this combination or with this combination or with this combination or with this combination, the whole thing inverted?
Yeah.
See, that's the same as just like a single variable or with a single variable, the whole thing inverted. The only difference is we have a combination instead of like a single variable.
Yeah.
Okay,
So you're looking at like this like whole thing.
right, right,
Single product.
right, because DeMorgans is valid whether the inputs are just a single variable or if they're a combination of variables. It's still valid, yeah.
Okay.
Does that help?
Yeah.
Okay, all right, but the next thing is, can you see that we just look at each one of these terms? Like if you just look at this, can you see that's a NAND gate, right? Because it's not C, ANDed with not G, ANDed with not S, the whole thing inverted. Right, same thing here, not C inverted, ANDed with not G, ANDed with S, the whole thing inverted. That's a NAND. So you see each one of these, each one of these is a NAND. So you see each one of those is a NAND. And what does DeMorgan tell us that a NAND is equal to? See, that's the other part of DeMorgan's.
Or with inverted inputs.
Right, and an OR with an inverted input. So see, we're gonna apply this part of DeMorgan's to each one of these terms, these NAND terms. So I take each input, invert it, and then OR it. So you see, I take, looking at this here, I take C, right, because I invert not C. I OR it with not G, and then I OR it with, what? OR it with G, because that's the inverse of not G, and then OR it with S. Right, and I do the same thing here. So it's going to be C or G or not S. And then same thing here. So not C, not G, S. And then not C or with not G or not S. Right, so does everybody see what I did here? I took this NAND and I wrote it as an OR with inverted inputs. See, I took each one of these inputs, inverted them, and then ORed them together. Right? You can see I'm doing it for each term. Well, when you're done here, right, after applying DeMorgans the second time, this is POS. This is product of sums, because look, sums ANDed together, which again, if you look at this as a base 10 equation, product of sums, right? It's really these being ORed and then ANDed together. But again, if you look at it as a base 10, right, you would say it's product of sums. Right, so you see, to go from POS or excuse me, to go from SOP to POS, you're applying DeMorgans twice. And once is this, and then the second time is the other part of DeMorgans. Now, just look at what we started with. Okay, let me take the red away. Remember, before we inverted both sides, we started with SOP for not E, right? So we started with this. Compare what we started with to what we ended up with. Like compare these two equations here. Compare this not E SOP and this POS for E.
It's inverted.
Okay, everything's inverted. What else? See, everything gets inverted, right? See, that's why we had to start with SOP for not E, to see it gets inverted. So if you want POS for E, that's why you got to start with SOP for not E, because everything gets inverted. But you know, the E gets inverted, C, G, S all got inverted for all these terms. But what else happened?
Multiple products to summing.
Right. Ands went to ors went to ands. Okay. So if you want to go from SOP to POS, invert all the terms, change ands to ors and ors to ands. It is the same if you go the other way, right? See, if I go from POS to SOP, it's the same thing, right? I invert everything and I go ors to ands and ands to ors.
So it's kind of like a double negation.
Well, a double negation happened here, you know, when we were doing the derivation, but I mean, it's not the same as when you know, not both sides. It's just that, you know, after you do the derivation, it just comes up to that relationship. That now that you've seen the derivation, you don't have to do it every time. Like you might want to do it once just so, you know, maybe you have a really good understanding of it, because, you know, you can watch somebody do it, but when you actually do it, usually, you know, it sinks in better. But if you want to quickly go from SOP to POS, just invert all the terms, change ands to ors to ands. Again, the most common mistake people make is that they want to get POS for E and they start with SOP for E. But if you start with SOP for E, you're going to end up with POS for not E because everything inverts. Okay, so when you want POS from a truth table, you look at where the zeros are. When you want SOP from a truth table, you look at where the ones are. All right. Okay, so this is a good point, I think, to take a little break, because when you come back from the break, these last few, this is going to go fairly quickly, and you know, the activity you can start, but let's take like a 5-minute break, and then we'll finish the lecture, and then you'll still have time to do the activity. Okay, so if you want to just go to the restroom or just relax for like 5 minutes.
That would be my bad.
So you have a specific project you're working with? Is it like, are you going to use like an Arduino to anything Arduino person to talk with, like the professor to see, you know, you might even be doing some interviews on Professor Boolean. I would contact him and just say, you know, it is so talking about it, and then maybe he knows of groups of students that see. I don't know if there's like a specific like Arduino club. Now there's different. What are you trained for? So you're just starting this. What is your first one? Yes. Oh, you're second year. Okay, well then you. Okay, well yeah, if you want to become more proficient at that, you know, that's who I. because he teaches, there's actually, I don't know if it's actually a class microcontrollers for everyone. It's, you know, it's open to all majors now. You wouldn't get credit. Like, let's go over here. But a lot of some just about, and they also Professor Bland, he built, like, he basically has two rooms. You have me. But I would say he's the department like expert in meeting. He uses it a lot. I mean, he's really good at coding. Okay. Sure. Okay. No. These two. I don't know. And you'll see why it's useful to me. But like, I guess the first one is the equation. So it's just that this combination, this combination, this combination. We don't have the. And you're gonna see that there's going to give us a lot of experience. Yes. Yeah. Because again, look at it as base 10. It's not really that. Right? But because it looks like that, it's
Open now, so
I think what we'll make it is we start up with the show the circuit diagram. Yeah, sure. Yeah. Now this, like I said, this is just a derivation. But the important thing you need to just notice is you can compare this to what you see why this is a product of So you might have to work with it.
So what is called?
Like,
Yes.
they more you
Well, you're gonna see in just a moment. You're gonna see that in the equation, we can get the diagram, the circuit diagram that shows. I think we can see that. Okay, so let's go ahead and start here. Like I said, it won't take long to get through the next couple of forms here. So the next thing we're gonna do is a circuit diagram. So a diagram that shows the logic gates that come from these equations. So let's start with the SOP. Well, look, this term here, what kind of gate do you think we're gonna need? An AND, right? Because it's this input ANDed with that input, ANDed with that input. So it's going to be a 3-input AND. They say you have a 3-input AND. Now, I'd have to put C through an inverter, right? Get not C. So you see, if I have C here on the other side of the inverter would be not C, then that would go to the NAND gate. Then G would go right into the AND gate. And then I need another inverter for S. Right, because I want to invert S. Right, so you see that this is an AND gate. What's this term? What kind of gate? Hey, that's another AND gate. In fact, we have 4 AND gates right here, right? Because to get this term, we need an AND gate that ANDs these 3 together, and then we need another AND gate. So you see we're going to have 4 AND gates. Right, and you would just have not C, G, S. You'd have C, not G, not S. We have C, not G, S going into that one. So all these AND gates would have 3 inputs. And I'm not gonna draw the inverters, but you understand you have to put the inverters there, right, to get the not variable. But you know, this would be not C, this would be G, S, then you have C. Not G, not S. Then you have C, not G, not S. And so everybody see why we'd have 4 AND gates, right? Because these 4 terms, the variables are ANDed together. Okay, what do you think is going to come next? What are we going to do next? Yeah, you just take these terms, because at the output of these AND gates will have the terms, right? Right, this AND gate that ANDs these 3 together, at the output, we're going to have this expression. And then here we'd have not C, G, S. Here we'd have C, not G, not F. And then here we have C, not G, F. Right, in those terms here, right, these combinations get OR together. So we just have 1 4 input OR gate. These would all come into an OR gate. And then at the output of this OR gate, we have this expression. Right? Because the OR gate's going to take each one of these combinations and OR them together. So you see, SOP, when you have an SOP equation, it gives you this logic circuit. This logic circuit gives you this equation. This equation came from this truth table. So this logic circuit is performing this truth table. It's a logic equivalent of my appetite for these 3 ingredients. Okay. Does that make sense? Any questions on that? Okay. Oh, question.
So the X of D, you put like put a not be, would you like us to do that?
Yeah, good question. Yeah, if the question is, if you look at the activity, the first one, I give you, now what kind of equation is that? What form? SOP. So yeah, I give you the SOP for F. And because my computer program, I couldn't do a bar. Yeah, I used the little tick mark. So for example, that first term for F is U, not B, W. Yeah, so I just used the tick mark because I couldn't do it on the computer. But yeah, when you actually write it, you want to put a bar, that's fine.
Okay, and if we can take more of that.
Yeah, that's fine. Yeah, either one. Yeah. Okay, any other questions on this diagram for SOP? Because if you understood this, what is POS going to look like?
A bunch of the 4s and together.
Exactly. It's just the opposite, right? SOP, you're ANDing to get the terms, then you're ORing. POS, you're ORing, then you're ANDing. Right? So you see POS, you're just going to have 4 OR gates. And they're going to have 3 inputs again. I'll let you fill in the variables. I mean, I'll do it if you have questions, but. And then the outputs of each of the OR gates will go to an AND gate. So you'll have a 4 input AND gate, and this is where your E would be. Now, you know, at this point, you might be wondering, well, why is it good to have these 2 forms? Like, why not just have SOP, or why not just have POS? Can you think of a reason why it's a good idea? It's good to know both of these?
You might have like more OR gates than AND gates.
Yeah, or more gates, just
Yeah.
more gates. Yeah, depending on your truth. Now here, it came out the same, right? Because they have the same number of 1s as the same number of 0s. But depending on your truth table, one of these forms might give you less gates. Right? And if you have less gates, it's more efficient, right? Because both of these circuits do the same thing. The reason why I know that they do the same thing is because they came from the same truth table. So these circuits are logically equivalent. They're going to give us the same result. So there may be a possibility where you have a truth table where one of these circuits, one of these forms is a lot less gates and it does the same thing. Right? And if you're going to do the same thing, why use more gates? Right? Okay. So that's the circuit, or yeah, circuit diagram. Okay, any questions before we move on to the timing diagram? Okay, now the timing diagram, and you can see here, I already started it ahead of time, so I'll give you a moment, like a couple of minutes if you want to draw this down. You may be wondering why I use green. I actually use green on purpose, and that's because when you check your simulation on Vivado, right, when you do your lab work and you go to test your design on Vivado before you download it to the board, because remember, you always want to make sure you have a successful simulation on Vivado before you test out your design on the board, because it's inefficient, to just skip the simulation and download to the board, because if it doesn't work on a simulation, it's not going to work on the board, and it takes time to generate a bit file. So why take that time if you know it's not going to work? And also in the follow-on class, CP 233, for the first 8 weeks, you're just doing simulation. You don't even download to your board in that class until the last couple of weeks when you got all, your microprocessor all built. And the reason I use green is because when you have good waveforms in Vivado, it shows the waveforms green. At least it defaults to that. I think you can change the color, but if you don't change the color, good is green. In Vivado, in the simulation, if your signal is either red or blue, that means something's not right. It usually means something's not connected right or something's not declared right. We'll talk more about that later. But another key thing that some students miss is that it's not enough for your waveforms to be green. I mean, that's the first thing, because if they're not green, something, grossly is wrong. Okay, but the waveforms can still be green and there can still be an error. You got to still check the data and make sure the data is right. Okay, so here's what a timing diagram for that truth table would look like, right? Because the way you verify your lab zero design is you make sure the simulation gives you the same truth table as you're expecting, right? You're given a truth table for that logic circuit, and you want to make sure that your simulation is giving the same one. And then you test it on your board, make sure the board's giving you the same, okay? So to make sure, like if this was a Vivado simulation and say that was the truth table that you were verifying that's working correctly, well, you see a timing diagram just shows you inputs and outputs versus time. And when you're looking at a timing diagram, t equal to 0 is over on the left side, and time progresses as you go left to right. So you see, if you look at this timing diagram and you look, say, at this time right here. Well, at this time right here, S is 0, G is 0, and C is 0. So if my design is working correctly, I should get an output of 0. Okay, so during this time, E would be 0. Okay, then see at this point, S goes to a 1 and the other input stays 0. So now during this time here, the S is 1, G is 0, C is 0. So if my design is working correctly, well, E should still be 0 during that time. Yep. There you go. Thank you. Yeah, because I think I'm out of view. Yeah, let's see. Thank you for telling me. See, I always forget. There we go. Thanks. Okay, so everybody see why this would still be 0? And then let's see, when does it, well, it'd be 0 up to this, right? Because it changes right here. Okay. And now at this time, right, our inputs change, right? Now we have a 0 for S, a 1 for G, and a 0 for C. So if my design's working correctly, the output should be a 1. So it should go up to a 1 at this point, right? So you just keep going, right? Because, here's the input is all zeros. Then you got 1, 0, 0, then 0, 1, 0, then 1, 1, 0. Right? And if your design is working, the output E should agree with your truth table. All right. So you see, that's how you verify your design on Vivado when you're looking at a timing diagram and simulation. You're looking at the combinations as they vary in time, and you're making sure that output agrees with what you intended. Okay. All right, so that's timing diagram. Okay, then there's a black box diagram, portion over here, black box diagram. And let's see. Okay, lab. I remember what. Oh, well, for the lab 0, we only have what, 3 inputs is there? Black box diagram. Oh, we'll do the black box diagram for this example here. Okay, black box diagram, as the name implies, you just have a box, right, a square. And the purpose of the black box diagram is that it shows you what the main inputs and the main output or outputs, depending if you have one or more outputs, is for your design. So for this truth table that we did here in class, we just have 3 inputs. So you would just show those 3 inputs and label them. And you would show the output. Label the output. So, and you usually give it a name, like we could give this a name, GP appetite. GP app, if you will. Notice I used an underscore. And I think I mentioned this last class, but I'll say it again because it's very important. Vivado does not like spaces in any sort of name, in the file path. So don't use spaces. Also, in this example I did in class, I just kept the inputs and outputs very simple, just one, letter variable. But when you do your lab work, now for lab 0, if you've already done lab 0 and you just use like A, B, C, D, that's fine. But get in the habit this quarter of using descriptive inputs and outputs. Okay. Like you might want to do something, well, for the first couple of labs, lab 0 and lab 1, I would just use single variables like we have been in class. So later on in the course, when we start using like multiple modules instead of just one module, you don't want to call the inputs the same thing for all the modules. Like say you have 3 modules, you don't want to keep using like ABC for inputs and, F for output. You want to be more descriptive. Like say one of your modules is named decoder. Okay, you'll see what a decoder is later on this quarter. But you might want to put like DEC underscore A, if it had like an A input. Okay, instead of just putting A. And the reason for that is because once you have, more than one module, if you keep using the same name for all the modules, when you go to look at your timing diagram, you're going to have a bunch of waveforms that are all labeled the same. And you won't know, well, does this A go with this module? Or does this A go with this other module? So it's more just a bookkeeping type of thing, okay? Now, in this class, we don't get that crazy as far as how many modules in a design. Like I think the most you'll have is maybe 6 or so. But when you do the microprocessor in CP233, you're going to have like a dozen or more modules. Okay, and it gets really, hard to bookkeep in that class if if you're not descriptive with your names. You have a question? There's not really a standard. I mean, I think most people kind of take the name of the module and then do underscore and then whatever the input is. I mean, that's the most common thing I see, but there's not like a strict standard or anything. Yeah, it's more personal preference, whatever, works for you. Okay, so that was black box diagram. The last question.
Kind of hard to see from here, but what is the thought with the black box in it? Like you're saying?
Oh, I just gave it a name. I just put GP underscore APP for Gary Perk's appetite.
Oh, gotcha.
Yeah, but you can name it whatever you want. But yeah, you give your black box diagram a name. Like you could give lab 0, for the lab 0 black box.
Okay. That was thinking.
Are black box diagrams the same diagrams that you use for like op-amps? What was that?
Well, no, and op-amp, you're talking about when you, just to make sure I understand your question. So you're saying, like the op-amp symbol like this with the plus minus, is that what you're referring to?
No, like usually like it'll have like a diagram for like the actual like chip and stuff.
Oh, okay. Yeah, that's sort of like a black box diagram. Yeah, I don't know if it's called that, but yeah, you're talking about the one that shows like the pins. Yeah. Yeah, I don't think that's technically a black box diagram, but it's the same idea. I think they just call it like a parts layout or something.
Yeah.
What's that? Or pinout, yeah. Okay, any other questions? There's just one more thing, and then you can do the activity. The last thing is what system Verilog code would look like for SOP and POS. So let's look at this one here. Okay, so if I was going to write the code in System Verilog for this Boolean equation, the way I would do it is first you use what's called a sign. And then you put the output, so we put a sign E, and then equal. And then what I would do is in parentheses. Okay, now in System Verilog, a bar, not in a Boolean equation is a tilde. Okay, that's the little squiggly line. It's let's see on your keyboard, it's the symbol above the little tick mark. So if you look at a keyboard, the key to the left of 1, the tilde is the upper one. So you'd have to do like a shift that key. Okay, so it'd be a tilde. It's not a dash, it's a tilde. People make a mistake and they put a dash sometimes. And then you would put the variable. Okay, so that would be like not C. And then in System Verilog, and is the ampersand. So if you look at the keyboard, it's the symbol above the 7. So you'd have to do a shift 7. Okay, it's ampersand. Like that. That's the and. So to do this term, you'd have not C, the not is the tilde, then anded with G, and then anded with not S, so tilde S. Okay, so this here would be that term. And then or in System Verilog is the vertical line. So let's see, that's over on your keyboard, it's over to the right, it's above the slash. Okay, so you do vertical line, and then you just keep repeating. You do this next term the same way, then put another vertical for or and so on. And then you end it with a semicolon. Okay, so the last thing you would have is a semicolon. That ends the line, if you would. Okay? So POS is the same idea. It's just POS, you'd have C vertical line, G vertical line, S, and then, in parentheses, and then you'd have the ampersands between the terms, right? So just like we were talking about before, these are kind of like opposite. The Verilog equations would look kind of opposite to it.
So should we always write out someone like the SOP and the POS, or like is one of them where you split the other?
Okay, that's a good question. Well, are you talking specifically for Lab 0 or just in general?
Yeah.
Oh, in general. Yeah, in general, like I mentioned earlier, the reason to know why, or the reason it's good to know both forms is because depending on the truth table you start with, one form might give you less terms. And if you have less terms, that's less gates. Okay, here it came out the same, right? Because we had the same number of ones as zeros. So that's why, but yeah, if you had a truth table where you had more ones or more zeros, right? One of these forms would give you less gates. Yeah. Okay. Now, as far as the lab work, for this first lab, I'm just expecting you to write an SOP for that truth table that's given that you follow in Lab 0. But you're going to see that, it's the next lab, I think. I think Lab 1, we do ask you to do multiple forms. And these aren't the only forms. Okay? You'll see next week that there's a couple of other common forms. Okay, but this is all that you need to know at this point. Okay, so that's the lecture. That's all that I want to cover with the lecture. So the next thing is to do the activity. And like all activities, group work is encouraged, but each student do their own work. The answer is up on the board over there on the wall. Okay, so you can check your answer with mine. Oh, one other thing I wanted to mention about the lab work is this was a question a student emailed me that I wanted everybody to know the answer to. And the question was, last time I talked about how for successful design, you don't want any errors, right? So you should have no errors, no Vivado errors. And then you should have no warnings that have the word latch. And then in the lab criteria, it says, no warnings with the word latch or other significant warnings. So the question was, well, what do you mean by, significant warning? Well, you look at what I have written up here, you might want to take a picture of this at some point. Like I said just a moment ago, you don't want any errors and you don't want any warnings, including the word latch. Okay. If you have other warnings, so let's say that you have additional warnings that don't have the word latch in it, and you're wondering, well, what are these warnings significant? Well, if your simulation is successful, and if the design works on your board, those other warnings that don't have the word latch, they're not significant. Okay, they would only be significant if your simulation wasn't working correctly and or your design wasn't working on the board. Now, it is possible in this class that you can have a warning with the word latch in it, and you can still have a successful simulation, and you can still have it working on the board. But like I have written up there, that wouldn't be acceptable. Okay, we don't want you to have the word latch in any warnings. Now, later on in the quarter, it's going to be several weeks from now, we'll talk about what a latch is, and I'll explain more fully why it's like that. Okay, but treat a warning that has the word latch in it like an error. Okay, even though your design might work.
So I tried Lab 0 and I couldn't find a constraint file anywhere on the Canvas or anything. Where am I supposed to get that?
It should be there. Yeah, I can check once it's
It's under modules.
It is?
Yeah.
Scroll all the way down.
Yeah.
Okay.
Yeah, your question brings up something else I want to emphasize. Please, if you haven't already done so, go to Canvas, under modules and look at all what's there. There's a bunch of stuff there. Yeah, so. Okay, but like I said, you can work on the activity now. Remember, you need to turn in the activity before you leave to get credit for it. And then once you're done with the activity, you can use the remainder of the time to work on Lab 0. Lab 0 is not due until tomorrow at midnight, so you still have some more time if you don't finish in class today. Also, one advantage of an 8 to 11 class in this room is that there is no class in here from 11 to 12. So if you wanted to stay past 11, you can. I'm going to be in here eating lunch. And also during the lab portion, like I said, you don't have to stay in the room if you don't want to. If you want to go back to your dorm and work on it or go somewhere else on campus and work on it, that's fine. Okay. But the activity is the next thing to do.
I know. Like having your hands kind of